This is the February edition of our regular monthly seminar series on the use of data science in all kinds of research for the Live and Know Centre for Doctoral Training. And we happen to be joined today by Felix Yu, who's a fourth year PhD student, again from the University of Harvard. And he's going to be talking to us today about his research into improving neutrino telescopes using machine learning. So whenever you're ready, Felix, please get started.
Yeah, thank you very much. So yeah, I'm happy to be here to talk about using machine learning in neutrino telescopes. Um, yeah, so firstly, I guess just to sort of motivate neutrino telescopes, let me just start with the sort of broader problem of these high energy cosmic rays. So cosmic rays are essentially just ultra high energy protons or sometimes nuclei that reach energies far beyond what we can produce here in terrestrial accelerators. And so despite having measured them for over a century, their astrophysical origins are still largely unknown. And this is mainly because these are charged particles, and so their trajectories are sort of strongly deflected by magnetic fields during propagation. So, if you look at this figure on the right, they get produced, and then because they're affected by the magnetic fields, they sort of, curve around for a bit before reaching Earth. And so that sort of erases any directional information on where they came from. So the leading hypothesis right now is that these particles are sort of accelerated in very extreme astrophysical environments like black holes, such as active galactic nuclei. Um, and importantly, those same sort of hadronic uh, acceleration processes that produce these cosmic rays should also produce these secondary messengers like gamma rays and neutrinos. So the gamma rays are actually also an important probe, and they do point back to the source of where they came from. However, they can also be absorbed during propagation, and then these also can be produced by purely electromagnetic processes, which sort of complicates their interpretation when they are detected here on Earth. So the neutrinos, on the other hand, are really unique messengers because they're both electrically neutral and they only interact via the weak force. And so they essentially travel undeflected and unattenuated from their production site all the way to Earth. And what this basically means is that when we detect a high energy neutrino, it carries a lot of very direct information about what is happening deep inside the source. And hopefully that can give us more information about what is going on in these sort of extreme environments to produce these cosmic rays. And so neutrinos are sort of key to sort of messengers for probing these sort of high energy processes. So the largest neutrino telescope in operation right now is called IceCube. It's in the South Pole, so in Antarctica. And to sort of put, I guess, this field of neutrino astronomy in context, it's sort of useful to look briefly at how the field has progressed in IceCube. Um, so, so what you see here is sort of a very condensed timeline of this. So, the idea of a telescope in the Antarctic ice sort of dates back to the late 1980s. And the Amanda detector was sort of completed in 2000, which sort of provided a first proof of principle, and they used these to actually detect these so-called atmospheric neutrinos, which are neutrinos that get produced when these cosmic rays hit the atmosphere of the Earth. Um, and so IceCube itself was completed later in 2011. And then only a couple years later, they were able to sort of detect the first sort of diffuse flux of astrophysical neutrinos. And then since then, the field has sort of steadily transitioned from detection to astronomy. with increasingly more sort of source associations. So starting with the in 2018 this TXS Blazar, and then more recently the neutrino emission identified from this active galaxy NGC 1068, and also the Milky Way itself. So the key question now is how do we continue to make progress from here? Um, so I guess there's sort of three very high level uh methods that we can do. So the first is sort of obviously to improve or build new hardware, so larger detectors, and next generation experiments. But of course, that comes with a lot of budgetary and engineering constraints. The second, obviously, is just to pass time and collect more events. And this is really important because collecting more data increases statistics, which is really important since the neutrino interaction rates are extremely low. But obviously we don't have much control over that. And the third approach, which is sort of what I'll focus on today, is improving the software size of the analysis. So this includes better event filtering and selection and better reconstruction, and sort of just more efficient use of the information that's already contained in each event. And this is sort of where the machine learning side of things comes in. And then, these last two significant discoveries by SQ was actually made possible through this using these ML-based filtering and reconstruction techniques. Okay, so let me just briefly outline how the talk will be structured. So I've sort of organized it to follow like what typical stages of a neutrino telescope analysis pipeline would look like. So first, like this is just a very high level overview, but we have like the detection of the neutrino telescope, and then generally we'll have like we want to use like these very fast and efficient machine learning techniques to sort of do like filtering of events and selection of events. Um, and then finally we do like the we use potentially more computationally intensive methods for doing the full event reconstruction. And so on the right are just specific projects that I'll focus on in this talk. And these are sort of projects that we worked on. And so in the filtering stage, I'll discuss how we use these, or I'll discuss efficient point transform-based models for this spatiotemporal data, designed to sort of operate with light hardware constraints. Um, and in the reconstruction stage, I'll show how the self-supervised learning can be used to sort of reduce the sensitivity to simulation mismodeling and unknown detector effects, which are sort of a major source of uncertainty currently with the ML-based methods. Okay, so I'll start with part one by briefly describing how these neutrino events are detected and represented in the telescope before moving on to the ML stuff. So the detection principle is quite straightforward, I guess. So what these neutrino telescopes essentially are is just a very large volume of instrumented natural medium. So typically you want something, well, typically like they use something that is, abundantly available and also has desirable optical qualities. So usually water or ice, like in Ice Cube's case, they use ice. And they instrument these huge volumes with these photon detectors. And the idea is these neutrino interactions will produce charged leptons, which in turn emit this Cherenkov radiation. So like for example, here in this figure, we have like a neutrino coming in, which is initially invisible, but if it interacts inside the rock or in the ice or water or whatever, it will produce its associated lepton, and this is something that we can see because it's charged, and it, as it propagates, it produces what's called this Cherenkov light, and this is sort of this blue thing that you're seeing here, and these are photons that will be picked up by the sensors in the detector. So essentially what it is that each event is sort of observed as like a pattern of spatiotemporal photon detections across thousands of these sensors. And yeah, here's just a little nice animation of a simulated event in Ice Cube. So this is also like a muon that goes through the whole detector. And as you can see, we sort of use like the color scale as a indication of like the timing of the event. So these red hits are like earlier and the blue ones are later. So you just see like this muon is coming through and it produces all these photons, which are the yellow tracks. And then some of them eventually hit like the sensors and get picked up. And then yeah, you'll notice also that like the photons in the ice especially, they don't take very straight paths, so they're like going all over the place, and this is due to like the scattering. And this is sort of why like things like trying to reconstruct the direction of these events, and trying to point back to where they came from is sort of is not that trivial, even for like a really idealized event like this one is. Um, yeah, so more specifically, like these photosensors record a distribution of detected photons or charge as a function of the detection time, or as a function of time. And so, we're looking at again one of these event displays, and then if we zoom in on some of these sensors, or they're called DOMs in IceCube, we sort of see like each of them has like one of these distributions of detected photons versus time. And so some of the sensors see a lot of light, a lot of photon detections, and others not so much. Um, this one, for example, these sensors were very close to the interaction point, so they saw a lot, but some of the other ones that are farther away don't see that much. Okay, and then just very quickly, so there's like uh I guess three main sort of patterns or morphologies that show up in these events. And it depends on like what the interact neutrino interaction that produced them was. So these charged current new mu interactions produce what's called these track-like events, and this is the thing that I was showing you in the animation just now. It sort of creates a nice looking track here that's very important for our source searches because they have generally have much better directional reconstruction. Um, and then we have like these neutral current or new ACC events that create what's called these cascade-like events, and these are show up as like blobs in the detector. And then more rarely, we have these charge current and Utal events that can create these double cascades, which kind of look like two blobs um, next to each other. Okay, so how do we sort of represent all this timing and charge information on each photosensor? And specifically talking about how like we represent them for our neural networks later on. And so we have kind of three main options here. Oops. So we could use the directly like the waveforms that get recorded in these photosensors. So essentially just directly taking that distribution of time or of charge and photo detections over time. And the problem with this is that they become very long and variable length. And so also they're kind of hard to get your hands on because of the bandwidth limitations. In the South Pole, they don't actually record or send back all of the events with the full waveforms because they take up so much space. Um, so the other option we have is to use like these pulse series, which are sort of extracted and simplified from these waveforms. The idea here is like, you can sort of try to have like, you can kind of algorithmically sort of try to tell how many like photons created like these peaks in the waveform, and this is sort of what the pulse series are. But these are also variable length unless they're padded. And then finally, we have like the summary statistics, which essentially are just nine sort of important statistical variables that is derived from this pulse series. And so the nice thing about this is that they're very compact and also fixed size for every DOM or every single photosensor. And so very convenient to use for like machine learning applications. And so when we talk about these ML applications, we're sort of mostly working with these two things just because the waveforms are not very convenient to use. Um, okay, so I'll move on now to talking about these efficient point transformers that we have been working on. Um, and so just to kind of motivate this, so these neutrino telescopes see a lot of events, and that's because they're sort of dominated by these atmospheric backgrounds. So for example, this is just the event rate here on the y-axis. And then these are three sort of different neutrino telescopes that are either operating right now or they're building it right now. And for IceCube, like the event rate or the trigger event rate is like almost 3,000 hertz per second. Or sorry, 3,000 hertz, so 3,000 events per second. Um, and so and of those like 3,000 events that get recorded every second, the atmospheric muons outnumber the neutrino events by orders of magnitude, and they form the primary background when we're doing any neutrino-based study. So the ratio goes about like 1 billion atmospheric muons to about 1,000 atmospheric neutrinos to about one astrophysical uh, neutrino. And so these efficient machine learning based methods are really important or even required to sort of process, billions of these events that have been collected over more than a decade. And we have to do them intelligently because we don't want to accidentally throw away any of these precious neutrino events. So this is sort of the reason why the I guess first approach was to use like these convolutional neural networks. So they're these CNNs are extremely efficient and they've already been used in IceCube. For example, for that galactic plane analysis that I mentioned earlier. Um, and this is sort of the way that they set it up, in a way that where like each DOM or each photosensor sort of serves as like a pixel. Just because CNNs are sort of designed for regular grid-like structure and like image-like data. But there is sort of like a geometry mismatch that is a little bit dissatisfying to use because you have to do all sorts of, convoluted things to try to get this data structure to work, I guess. There's like lots of padding and like um, you know, splitting of the event into like multiple parts and such. So there's a bit of a geometry mismatch here. So we've been trying to move on to, or well, people have been moving on to these transformer-based models, which, I'm sure everyone knows that have seen a lot of success in many other fields. And so these transformers work on sequences. So they take in like a sequence of these tokens, and the events sort of provide us a pretty natural way to try to tokenize these events. So specifically, we can use like the spatial and the temporal properties of these photon detections to provide a sort of natural way to tokenize events. So we can use like, well, you can imagine like the first token would be like a group of hits that, were spatially clustered and happened close together. And then like each of these would have their own features and then you would feed them into a transformer and, process them that way. Yeah, so more specifically, we sort of designed this point cloud-based transformer model inspired by methods like point transformer and point MAE. And there's sort of two main modules here. Oh yeah, we call this Neptune, which stands for an efficient point transformer for ultra relativistic neutrino events. Um, And so there's sort of two main modules to this Neptune architecture, which is the event tokenization step and then the transformer encoder itself. So the input data to the tokenizer is the summary statistics representation of these events that I mentioned earlier. So this is what you're seeing here. So for each of these events, we have its three spatial coordinates, and then we also have an associated feature vector with each of those coordinates, and that is the 9 summary statistics that represents sort of the timing and the charge information. Um, and so during the tokenization step, um, importantly, so we set like this T max parameter here. Um, and so if the number of hits and sort of exceeds T max, um, then we actually use like this FPS or KNN algorithm to sort of downsample and pull features together into these patches or these tokens. And so the Tmax parameter is able to set like this transformer input length. And because of that, this is sort of the main sort of hyperparameter that you're controlling if you want to control the trade-off between speed and uh, performance. But also this is really important because in some of these events, especially like the high energy ones, the detector gets like blown up with light and there's a lot of detections. And so what happens is because the transformer scales so aggressively with the sequence length, it sort of like slows down the network inference a lot. And so if hit DOMs exceeds that Tmax parameter, we can use FPS, which is, I have sort of a visual representation of what it looks like in 2D here, but it basically tries to choose, you know, points such that they're very spatially, how do I just, like, it chooses points so that, it sort of maximizes the distance between each point, I guess. And so what you end up with is like, with, very good spatial coverage of the initial point cloud. And then the idea is to like take those points and then you use KNN to sort of get the nearest neighbors and then pull them together. And so if this threshold is also not hit, then each hit DOM or each hit photosensor is sort of acts as like its own patch or its own token. So yeah, so these sensors or these DOMs, whether individual or grouped via KNN, can then be processed into tokens, which are then fed into the transformer. Okay, so how does the reconstruction performance look? So yeah, again, like one of the most important tasks we have for RICO is these directional reconstruction of the track like mu events. So what you're seeing here on the uh, right-hand side plot is a plot of the angular resolution or the angular error as a function of the true neutrino energy. Um, and so the you usually see these trends in these kinds of plots where like the resolution will be high at low energies and then fall off because as you get higher and higher energy you generally have more information and more light to sort of reconstruct the event. Um and then I also shaded these regions just to denote like this is sort of the energy regime where the you're sort of astrophysical neutrino dominated, and so it's actually really important to be able to reconstruct these at the higher energies. And so you'll see that the Neptune performance sort of at these high energies sort of scales with this Tmax parameter. So each of these different lines I vary the sort of Tmax parameter while sort of keeping like the same receptive field, if you will, by like also increasing this K parameter, which is like the number of neighbors that the KNN uses. And so you see by increasing that Tmax, you get better performance at the higher energies. Um, but of course, the trade-off is the runtime or the efficiency. So generally speaking, like if we run inference on CPUs, the runtime is sort of in the on the order of like 1 to 10 milliseconds, which is comparable to existing CNN and traditional reconstruction methods. But you can see that there's sort of a clear scaling again with this Tmax parameter due to the transformer overhead. Um, yeah, and so like so for example, like the Tmax, or for example, the model with the Tmax equals 32 takes like 7.5 milliseconds median. Whereas for the 256 model, it took about like 40 milliseconds. But the cool thing about this is that this is actually feasible to process most of the stored ice cube events, even if you, um, have only 100 CPUs. So the time it takes, I just included in this table, the time it takes to process 10 billion events with 100 CPUs in days. It takes like about a week it would take about a week for like the smallest model. But maybe if you throw in a couple of GPUs in there, that would help you not have to wait for so long. But this kind of shows that we can sort of use these types of models for event selection and filtering in really early stages of the data pipelines, which is cool. And also without having to fully rely on GPU inference as well is really useful for um, existing infrastructure and budgetary reasons as well. Um, okay, so now I'll switch gears a bit and talk about this other project that I've been working on, which is trying to see if self-supervised learning can actually help us mitigate the effect of unknown detector effects. And so just to sort of set the stage again, so the state of machine learning in these neutrino telescopes right now. So all of these like ML-based reconstructions, including the one that I just talked about, are trained with simulated data via supervised learning. And so this approach is effective, but obviously because it has been used in IceCube before. But there's always this inherent concern that the simulations are imperfect, and that's very valid and very true, especially in these neutrino telescopes that are sort of embedded in a natural medium. For example, in IceCube, they put these things in like the Antarctic glacier, and there's all kinds of not so well understood stuff about the optical properties of the ice in there, just because there's like dust and there's like dust layers and there's other impurities that sort of heavily affect the attenuation of these photons that are our detection signal. And so these systematic uncertainties and unmodeled effects in real data are sort of remaining a key concern when we use these ML-based models that have been trained on simulation, because they can cause sort of this data MC disagreement where you train and you test your model on like MC or like simulated data, and then you try to use it on real data and you get either unexpected results or like worse performance than you were expecting. And so, what we wanted to explore as a potential solution is self-supervised learning or SSL. And the basic idea behind the SSL as opposed to supervised learning is, um, essentially you would, uh, instead of just train directly on like labeled simulated data, you would first pre-train on unlabeled data, and then you can fine-tune later on a labeled task for some kind of downstream task. And the key idea is like the majority of the learning would occur on the unlabeled data. So for example, like this again has been a really well explored topic in like computer vision and whatnot. And so they use these for images. So one effective pre-training method that they use on images is called like masked image modeling, where you have like some kind of input image and then you purposely like mask out certain features, or like you purposely mask out like parts of this image, and then you feed that masked out image to an encoder, and then you have a decoder basically reconstruct the or reconstruct or recover like the lost information. And the idea, I guess, is, well, the idea is if you sort of make that masking ratio like high enough, this becomes a pretty non-trivial task, and the network really has to understand what these images mean, and what the data in your data set mean. And so it has to really learn a lot of useful feature extraction techniques in this pre-training process on unlabeled data. And then you would fine tune later on the labeled data, and it would be able to do well even without like um, you know, a whole lot of training on unlabeled data. And so the idea or the connection here is that we actually have an abundance of unlabeled real data that don't have any systematic effects or any unmodeled effects like the simulations do. So the question we want to answer is, well, can the self-supervised learning, if we sort of pre-train on real data and um, fine tune on the simulated data, can that actually mitigate effects of data MC agreement disagreement in these neutrino telescopes? And so what we did as sort of like a proof of concept study first is sort of answer this. We tried to construct like a very extreme example by entirely omitting one of the most noticeable systematic effects or detector effects, which is like these uncorrelated noise hits from our simulation. And we want to study like what effect that would have in both the supervised and the SSL scenarios. Yeah, so first to perform this sort of study, or to perform this sort of experiment, we need kind of a baseline model that's sort of capable of both these supervised and these SSL training objectives. And so we can use like this Neptune model that I talked about in the previous section, which sort of provides a natural baseline because, um, yeah, so it enables like the same sort of concept from mass image modeling to be adapted to these neutrino telescope events because of this sort of whole event tokenization process. Um, so yeah, so we have like these tokens of which are like these patches of hits. And each of them have again like these their features, which include like the charge and timing features, as well as like an associated spatiotemporal coordinate. Um, and so in the supervised case, we would this was pretty simple. We would just aggregate all these token features. We would throw them into the transformer, and then we would get some kind of downstream prediction, which we can compare against like the simulated event labels. Um, but so for the SSL pre-training case, what we actually want to do is we just want to or what we tried doing is masking out the spatial and temporal information, and then try to recover and reconstruct that masked info, which is sort of analogous to this masked image modeling idea from images. Um, yeah, so the pre-training tasks are analogous to the masked image modeling. And so the transformers are trained to recover that spatial and temporal information of tokens. So again, this is like the same exact architecture. This is the same exact tokenization process. And then we sort of get to this transformer step. And instead of like giving the transformer like the full information, we purposely mask out some of the spatio-temporal, or we also tried like temporal only. We mask out like some ratio of the coordinates here, or the coordinate information here, and then we throw it into the transformer. And then the job of the transformer during the pre-training step is to recover that lost spatiotemporal information. Um, and so to talk about like the data sets to conduct our experiments, we set up a sort of quote unquote like fake data and simulation subset for each of our data sets. So, the important thing is like right now, since this is just a proof of concept study, all of these events are actually simulated, but the key thing is that we never use the labels from the quote unquote data set. And so we have two sets of data sets that we tried for two different downstream tasks. So firstly, we had like the track-like events for directional reconstruction, which, again, uh, I talked about this a bit. And then the other task that we, wanted to see if this could do is classification task between the single and the double cascade morphologies that I, again, showed previously. And this is a thing where like one of them is like looks like a blob in the detector, and then the other one looks like two blobs, which is kind of a non-trivial task because most of the time the two blobs are like really close together, so it looks like one. Um, but yeah, so in the supervised sort of the process for doing the supervised um, scenario is pretty simple. Like we just do a labeled training on the simulation subset as usual, and then we test or we run inference on the quote unquote like data subset. Um, and then for the SSL case, we have like this extra step where we pre-train first on the data subset without using any of the labels. So we do like that masked modeling technique. And then following that, we do like a labeled fine-tuning on the simulation subset, where we actually give it labels. And then again, we infer or we test on the data subset. Means like you have enabled them to train. So the first thing you can do is like what's called like linear probing, where you sort of freeze all the weights in the transformer and you just have like a linear classifier at the end of this to do your downstream task. And in this case, the only thing that would be trainable or updating is like the weights of this linear classifier. And this prevents catastrophic forgetting, but it also doesn't it really hurts your performance in the downstream task because you're not letting the transformer update its weights and you're only letting this sort of simple classifier do. Um, and the second option you have is to whoops. The second option is just to like have everything like you don't freeze anything and you let the entire transformer sort of train. And this leads to that catastrophic forgetting problem where during the fine-tuning process, your transformer sort of forgets everything about the pre-training data, which this is due to the fact that you're letting all the weights update and then it just forgets everything. Um, and then the final option, which this sort of paper presents, that we found was really useful is of doing like this block expansion technique where you um, have the original transformer block completely frozen, but what um, you do is you just add an expanded additional transformer block to the original, and then you let that train. And then we additionally have like the linear classifier to do the prediction at the end. And this sort of prevents catastrophic forgetting while also maintaining the model capability to sort of learn the downstream task. Um, and so, yeah, like I mentioned at the start of this section, basically in order to differentiate between like the data subset and the simulation sets of our sort of experiment that we set up here is we sort of inject a inject a varied amount of uncorrelated noise hits to sort of differentiate between the two. And so again, we sort of chose to model this noise noise hits because they're sort of universally applicable to all kinds of different neutrino telescopes, and they're also very potentially harmful for downstream tasks if they're not modeled correctly. And so to get an idea of like how much noise some of these telescopes get is, um, 500 to about 600 hertz is sort of reasonable based on IceCube or like other concurrent neutrino telescopes in operation. This is sort of the difference that you see between like a 0 hertz like clean event versus the same event that has been affected by like 600 hertz of noise. And yeah, you can see like there's clearly some effect and some noisiness going on with the event here compared to the clean one. Okay, so what happens if we very unfortunately forget to add noise into our simulations at all, which probably isn't a realistic scenario, but just to sort of stress test this sort of setup here. So in this scenario, or in this sort of experiment, the data subset has some noise added, while the simulation subset contains absolutely no noise whatsoever. And so what happens here is you can see that for the supervised model on this directional reconstruction task, it performs well on the simulated subset, or the simulation subset. So it's about like 2 degrees angular error median. But then we see that the performance sort of severely degrades when we go to run inference on the data subset, which includes noise in it. So you can see it goes up to like 20 degrees. Whereas for the SSL case, this is the case where we've pre-trained on noisy data and we then fine-tuned on the simulation subset. We see it's significantly more robust, although it does also show some diminishment. So again, it's about like 2 degrees. So it's like the same performance on the simulation set, but then it's only like 5 degrees on the data subset compared to 20. And we sort of see the same trend here with the cascade classification tests as well. And then so again, here I'm again showing like the angular error as a function of the neutrino energy. And again, here we can see very clearly that basically across the entire energy range, the supervised performance on data is just severely degraded from the performance on simulation. So adding noise where noise is not modeled is just totally killing the performance for the supervised case, but the SSL case is a lot more robust, as you can see. And then so secondly, we test the case, which is probably a lot more realistic, where noise is sort of correctly modeled in both data and simulation. But this time the sort of noise rate is varied. So there's about 100 hertz more noise in data than in simulation. So in this case, we actually see that in both the supervised and the SSL case, the models are pretty robust to these changes in the noise rates. So they both perform about equally well in the simulation set and on the data set. And it's the same story goes for the SSL case. And this is something that we see across both the directional reconstruction task and the cascade classification task. So, the idea is that, or so the sort of takeaway message that we can get from that, self-supervised study is that these sort of unmodeled effects can actually severely degrade performance when they're absent from the simulation. And the worry is that there's sort of an inherent risk of these subtle or unknown detector effects in the neutrino telescopes. And so, these sorts of unknown unknowns, if you will. And this sort of SSL technique, as we've shown, can sort of offer a viable way to try to mitigate or protect against that risk. And so just a couple conclusions here again about the whole talk. So some take-home messages is that we've talked about some of these point cloud-based transformers, which are really efficient and effective for both neutrino event reconstruction and early stage filtering. And then, yeah, again, unmodeled effects in our simulations when they're absent can severely degrade the performance of our models, of our supervised models, and then SSL can sort of protect against that risk. And so yeah, that's all I had. So thank you very much for your attention.
Cool, thank you. Okay, do you have any questions in the room? Yep.
Thank you for your talk. I think it's slide 31 or 32 when you were talking about different ways of dealing with catastrophic getting. Yeah, 31.
Mm-hmm.
I was wondering how the additional block expansion was initialized and why we wouldn't do something like freeze every block apart from the last one and simply train the last block and then classify it.
Yeah, okay, yeah. So that's something that we also tried is like instead of just doing like something like linear probing where you freeze all the weights of every single block in the transformer, you only freeze like the first n or whatever, and you let like the last couple learn. But we also found that that doesn't um really maintain the capability of the model to learn downstream task. Um, and so yeah, so the block expansion is essentially the I think same idea, but add additional you add like this expanded block, so actually like the model becomes heavier. Um, and so I don't know what uh I would guess like that's the difference between the two. Like potentially like maybe like allowing the weights to update from the pre-trained model to the fine-tuning task for like any of the blocks that were trained during the pre-training. Like it sort of like hurts the performance. But if you like take that whole model um that you had and you like freeze that whole thing and keep it intact and just add like these additional layers to the end, it seems to help it um, sort of get this balance between not catastrophically forgetting and also being able to learn the downstream task. But that is something that we also tried, and we just found that it didn't perform as well as doing this.
Cool. Any more questions? Okay, I had a couple. So how concerned is the ice cube community at the moment regarding the imperfections in the ice, dust, and things as you mentioned? Like, does this put like quite a big error bar in any of the results coming out from ice cube?
Yeah, so I think the general consensus is that the ice modeling, like systematic uncertainties, is our biggest systematic right now. And so yeah, I would say they're it's kind of a big concern. And there's also been like a ton of like work being poured into trying to model the ice better. So like, and they have made like a lot of improvements. It's just like, maybe for like future experiments or whatever, if we didn't have to spend like 15 years like studying the ice and getting to like model it correctly just for like our simulations and our like machine learning models, that would be really nice. But yeah, I think it's still to this day, even with the ice modeling improvements, still constitutes the largest systematic for IceCube.
Is it at the point where it kind of damages the actual science coming out of ice cube? Like, what would you say are like some of the biggest sort of scientific outputs from ice cube to date? I mean, you were kind of talking about kind of compact object mergers and kind of things like that. Um, is ice cube kind of competitive, let's say, with the kind of thing that you're getting out of gravitational wave detectors, kind of gamma ray bursts, things like that?
Yeah, so I would say like so yeah, like some of the most recent work that IceCube has been doing is trying to like localize these sources, right? And they have done it for some of the brightest ones, but because like the angular reconstruction and the angular resolution is so important for those kinds of for the like pointing power towards like the potential sources, the sort of you know the data MC disagreement between like these reconstruction methods and when you apply them on real data is like affecting that sort of uncertainty towards or it's affecting like the power that you have to like sort of point back to them. And then yeah, there was also some other like examples of this from KM3net, which is like another sort of water-based neutrino telescope where they um saw like a really high energy event that was very interesting, but because of like sort of the systematic uncertainties associated with the reconstruction, like the modeling of like the the water that they had their detector in, that also really affected like the sort of level of certainty that their reconstruction had. And so that was kind of an issue there as well.
Right. So is the advantage of doing this in the ice just you can theoretically have as big a detector as you want, sorry, as big a telescope as you want, whereas with like a water-based detector, there's probably some engineering practicalities.
Um, uh,
So I guess with water, I mean, you can sort of put more effort in to try and make it more pure, whereas with the ice, you're kind of stuck with what you've got.
yeah, so yeah, that's true. So I think in general, like, yeah, the water is, so I think generally speaking in water, like you have less scattering of the photons, but you have more absorption. Um, and then in scattering, or sorry, in ice is like opposite, like you have less absorption because the ice is like really transparent in the in the South Pole, and you just have more scattering. I think in both cases there's pretty strict engineering constraints. I think it's probably harder to do it in ice because they actually have to like drill holes into the ice to like put these things down into like down into the ice.
Yeah, I
Um
think melt the ice in place, don't they? Then and let it refreeze around the sensors.
yeah, exactly. And that's also like that is also like a really big concern for the ice model too, right? Because they had to they like melt the ice first to like put the sensors down and then it will like refreeze. But then the ice that refreezes is obviously going to be it has different optical properties than the ice that has been there for like billions of years. Um and so that is very difficult to sort of model, I guess. Um but I think I guess yeah, to answer your question, I think there's sort of different trade-offs between water and ice-based telescopes.
Okay. Any more questions at all? If not, final one from me then. Um, do you look for inspiration in this work in other fields? Like I know that the nuclear industry probably look at similar kind of cascade events. Um, say like nuclear safety, or if you can imagine different areas of astronomy, telecommunications, what have you, looking for um, denoising like very noisy backgrounds and picking up like isolated events in uncertain backgrounds. So do you see applicability of what you're doing now to different areas, and also do you take inspiration from what's being done in different fields?
Yeah, for sure. Like so for like the Neptune like model that I talked about, we took a lot of inspiration from these point cloud processing methods. And I think this is uh maybe I'm getting this wrong, but I think that was mostly used for like these sort of radar or like LiDAR sort of like scans where you sort of have like a sort of 3D scanning of like different points of some kind of object.
Yeah.
And this is sort of where like the point cloud processing is very um important and necessary. So we took a lot of inspiration from those kinds of fields because I think these neutrino telescope events are more naturally fitting to like this sort of point cloud structure rather than like an image per se. So that's yeah, we definitely sort of take inspiration from other fields for that.
Cool. Well, thanks very much, Felix. I think we can call it there. So we'll just thank our speaker again.
Yeah, thank you very much.